Kawano from USP, State University of Sao Paulo. I know Alexandre for quite a while. Actually, we met first time when I was delivering a mini course here in IMPA, and it was the Colloquium of Mathematics.
Yes, yes.
The annual event of the Brazilian Mathematical Society. And Alexandre was trying to learn something about inverse problems. And he was very successful. He finished his PhD at USP.
Yes.
With Professor Paulo Cordaro, and now he's a colleague, a very productive colleague. Today he's going to talk about simultaneously identification of source, initial conditions, and asynchronous sources in the vibration problem of Euler-Bernoulli beams. Please, Alexandre.
Oh, thank you. Thank you, Antonio. Thank you, organizers. Thank you, both sides of the communities, mathematical community, engineering community. Thank you. It's a great honor and a pleasure to be here at IMPA. Well, I'm going to talk about the problem of uniqueness of identification of sources and initial conditions. For those of not engineering background, what's Euler-Bernoulli beam? An Euler-Bernoulli beam is like if you take a rod, you take a bar, and you can support this bar at the two ends, and you put some loading on the top of this bar. The behavior of this bar is the behavior of a beam. The way the points of this bar deflects is governed by an equation, a simple equation that we call Euler-Bernoulli beam equation. And this problem is a dynamic one. We put this bar, this Euler-Bernoulli beam, under a dynamic loading, and we ask if it's possible to identify uniquely the loads that we impose on this vibrating beam. For the mathematicians, this is the equation. It's a fourth order equation in space, second order in time, second order because of the second law of Newton. We have the initial condition for space and initial condition for the velocity, and we ask if it's possible to identify both uniquely. At the same time, we identify this function f. We suppose that g, all g's, they are known. We know g's. We want to identify f, and we identify the initial conditions. These are the boundary conditions. We say that the tips are clamped, they do not move, and they do not rotate. So here the tips are clamped, and we have the initial velocity, initial position, here the force, and the function of time. And we specify, we know G, and we specify that G must obey a condition. The condition is that this matrix, that is formed by the derivatives of G, of all functions G, at time 0, this matrix is invertible. And as far as the spaces we are using, the functions, unknown functions that we want to identify, they are in isobolar space H minus 2. So functions like impulse functions, they are included here. Even concentrated momentum, we can apply bending moments at points inside this beam. And from the point of view of engineering, this is a very let's say general problem, because we have any number. We can think f can be very, very general. H2 for engineering models is a very, very large space for practical applications. And the problem here is that we have asynchronous source. So we have several forces acting at the same time. So we ask if it's possible to identify these asynchronous forces. Because if we have one force, intuitively, we may guess that maybe it's possible, even if we have to identify altogether the initial conditions. But what happens if we have multiple sources? We are going to prove that indeed it's possible to identify the forces, synchronous forces, uniquely. It's a uniqueness problem. And initial position when the initial velocity is 0. So we cannot, and I'll show you an example, we cannot identify uniquely the asynchronous force with the initial position if we have also to identify the initial velocity. So the initial velocity must be known. And the data to identify all these functions is the knowledge of the solution of the problem in an open set, arbitrarily small open set. Physically, for engineers, we can even think, it's not the case, it's not a point, but it's as if we were observing a point during an arbitrary, very small time interval, and it's enough to identify the asynchronous forces and the initial position, all at the same time. Then I'll show you a counterexample. What if we take a function solution? We start with a solution. We start with u of this form, h function of time, times phi. We plug in the Euler-Bernoulli equation, see what happens to the right-hand side. The right-hand side is like this. And we see that if phi is 0 in an open set, let's say omega 0, in an open set omega 0, if it's 0, let's take a phi very smooth, but 0 in an open set, we can observe this open set for how long, as much as we want. U is going to be forever 0. U is going to be forever 0. So we cannot identify nothing. And initial conditions, if we plug in this solution and see what should be the initial conditions for this to be the solution. These are the initial conditions. We see that in this case, when we observe the data is only the 0 set. And the initial conditions are not null. Here's the right-hand side is not null. So we have a counterexample. Then we ask, well, in what conditions can we identify the right-hand side with the initial conditions uniquely? Well, having this counterexample in mind, I say that we are going to see that the initial, if the initial velocity is null, the set of functions, all functions satisfy a set of conditions. Then, if we have that this solution is 0 in an open set, time space is 0, then necessarily all functions in the right-hand side are 0. So this is rather technical. I'm going to focus only the ideas. What is the technique to prove this? The technique is to find a formal solution. We have explicitly a formal solution. And to obtain this formal solution, we expand it in eigenfunctions. So we consider an eigenproblem. We change a little bit the internal product here, a little bit, just a little bit. In fact, the functions all, the space is h to 0, but we change a little bit the internal product just to get a basis of eigenfunctions that is more convenient for us. And here, the important point is that we get a basis formed by eigenfunctions, orthonormal basis, and the eigenvalues, they grow, it's important, they grow like this, the n to the 4th power. This is important information. And using this basis formed by eigenvectors, we can express distributions in the dual space of h to 0. H minus 2, we express then by using this basis, this is classical, and then we express forces, the forces, and we express also the initial conditions, the initial velocity and initial position. So our unknowns become the set of coefficients here and here, the Aj and Wn and Vn. So can we identify all these coefficients? When we measure the displacement of an arbitrary small set, arbitrary open set in the bin for arbitrary small interval of time. This is the question. Then, as I said, the strategy is to get first a formal solution that is obtained by an expansion in eigenvectors. It's just for checking things, what's the space where the solution is. The displacement is continuous with respect to time, and checking everything. The solution of this direct problem is unique, well behaved, and so on. And we work on the formal solution to put it in a more convenient way. And just manipulations, and we arrive at this form. This form is going to be important. So if we have a function written like this, which is obtained when, from the original problem, when we get a formal solution, and we write the solution by using an expansion in eigenvectors, base of eigenvectors. This is what we get. Then here is the question. If W is 0 in an open set time space, arbitrarily small, can we say that W is 0 and F is also 0? All F's are 0? That's the question. The information of the velocity is here in F0. Space, initial position, and initial velocity, they are here. So, but this is the mathematical question. Can we say that if W is 0 for in an arbitrary small open set, can we say that all coefficients here are 0? This is the question. And to answer this question, we have a tool. We are going to use almost periodic distribution. And just to remember some facts, some concepts, we recall that a sequence is uniformly discrete if there is a delta such that for any pair of elements of this sequence, no two elements are closer than this delta. It is uniformly discrete. And this can happen, this is for engineers. This is very important. And we don't know because if a sequence is uniformly discrete in general, because it can be 1 billion and then 1 billionth and 1, it gets closer than a specified delta. It can happen at any moment. So it's a condition. Our sequence and lambda here is a sequence of our exponents, the exponents of exponentials in our problem. And these lambdas are the eigenvalues of our problem, and they grow of the n to the 4th power. And this is important, n to the 4th power. So they grow fast. Another important concept that I recall is a set, the Pauli-Wiener space, which is formed by functions in L2, but when they have compact supports. We take Fourier transform, and we obtain the Pauli-Wiener space. This S here means the set where the functions, the original functions F, they have supports. They have supports in F. We take Fourier transforms, and we get the Pauli-Wiener space. We are interested only in the case of dimension 1 because here we are going to use it for the time variable. So in principle, this problem could be also a problem in a solid in 3 space or a plate in 2 space. But whatever problem it is, we use dimension 1 because we are going to deal with time. And other concept is the density of uniform discrete set. So this is our uniform discrete set. Our lambdas they are uniform discrete. And the density, the upper uniform density, is obtained by looking at windows of length C. We take the density, we take the number of the elements in this window divided by C, so we get the density in a window C. And then we take the limit and pass to the limit C to the infinity. So this is the, more or less intuitively, the density of lambdas in a very large window. The maximum density we get in large windows. And we have a result, we say that a set is an interpolation set for the Pauli-Wiener space if whatever sequence in L2 can be interpolated by functions lying in the Pauli-Wiener space. So we have a sequence C, N. Then we can interpolate this sequence by using phi in the Pauli-Wiener space at points lambda. And we have a result that says that if the upper density is lower than a certain value, then this set of lambda, set of points, it is an interpolating set for the Pauli-Wiener space. So you can interpolate the set of eigenvalues of our original problem. And here is a lemma. This is a central lemma of this work. If we have a distribution like this can be not anymore a function, can be a distribution because it may not converge. If we have a distribution like this, lambda n grow, the sequence grows to the n to the 4th power. Lambda n's, the square root of lambda n's is uniformly discrete. And if we take a distribution like this, f like this, if the distribution is 0 in an arbitrary small set, open set, then the whole distribution is 0. And the idea of this is just to use phi, functions phi, C infinity C, test functions, and we take the Fourier transform of this phi. When we take a Fourier transform of this phi, it lies in the Pauli-Wiener space. And what's interesting that if we take if we apply this distribution to phi, the Fourier transform of phi, then it's the same as applying this thing to the Fourier transform of phi, and the result is just phi applied to the square root of lambda n, because it becomes a delta. The Fourier transform of exponential, like this, is the delta distribution applied to phi. So we get this. And since the Pauli-Wiener space is an interpolating set for, excuse me, the sets of this sequence is interpolating sequence for the Pauli-Wiener space, and C infinity C is dense in L2 0 to 0, then we prove that AN Sn is 0. Since Sn is a Hilbert base, then AN is itself 0. All AN, all the sequence is 0. So just a simple check to see if it's not very extremely small, extremely simple problems, if it's not easy to deal with. If we test this distribution f with a test function, the result is not analytic function, fortunately, because otherwise the result would be too easy. Then the main theorem. This is a condition for the hypothesis of the theorem. The sets of all the time functions, the functions that we know, that multiply the unknowns, space functions that are unknowns. This matrix obtained by G's and its derivatives, it's invertible. And F must satisfy this. F at time 0 is 0. And then if we have a distribution like this, which is the form, exactly the form of our formal solution, but here enters the velocity, initial velocity 0. When the velocity, initial velocity 0, we have this form. Otherwise, the form is a little different. So the hypothesis of 0 velocity, initial velocity enters here. When we have this form, then if this distribution is 0 in an arbitrary small open set, then all F are 0. So this is the main result. So what's the strategy? The strategy is to, in the end, use our lemma regarding F. And we have here just one equation and several unknowns. The idea is to get more equations. And to get more equations, we just we apply derivatives. But when we apply derivatives, fortunately, we get Volterra equation of second kind, which is a very good thing because it's 0. G is the kernel. If G0 is not 0, then Fj is 0. And we keep differentiating this equation. The problem is that we get more unknowns. Whenever we differentiate, we get the derivative of Fj and other derivatives, which increases the number of our unknowns, which we don't know, we don't want. So we apply this elementary fact to get rid of new derivatives, first derivatives. We get second derivatives instead. But the second derivative is related to our original problem because the second derivative of time is equal to the fourth derivative in space. And if we apply the Fourier transform in space, and we can do it because we can use the Fourier transform of test functions compactly supported in arbitrary small intervals in space, we get things like this. This is just the fourth derivative that converted in the language of Fourier transforms. And we keep doing this. There is a technical problem of the order, if it's even or odd. It's technical, I skip it. And we recognize that the hypothesis on G leads us to the fact that we arrive at something like this, a system of equations obtained when we differentiate the original equation, and we manipulate it by using Fourier transforms. And we get at this point, and we recognize that this matrix is invertible if the original matrix is invertible. If the hypothesis is satisfied, if this matrix is satisfied, then this matrix, which is related to the derivatives of the original G's, then this matrix is also invertible, and we can get rid of this matrix here by just pre-multiplying by the inverse of this matrix. And then we arrive at a Volterra integral equation of the second kind. And we prove that f, the Fourier transform of f, is 0. And we apply our lemma regarding the f in the form of a series, a distribution in the form of series. And we get all the coefficients are 0. This is just written off what I have said. Just to clarify, if the initial velocity is 0, then if this happens, then all hypotheses of the theorem is satisfied. Otherwise, the form is a little different. And we identify f. This is a little technical, but I just presented the idea. And then there is another condition that is used in this field of identification of forces and initial conditions, which is the final overdetermination. When we observe the final state of the beam, final position, velocity of the whole beam. Unfortunately, the whole beam. If we see the whole beam at the end, then we can reverse the time arrow, and we can identify the original space, position space, and original velocity, as well as all the functions, the loading functions f. The conclusion, just to sum up what we have seen, is that if we shown a counterexample showing that it's not an intuitive problem, we can construct counterexamples in which the unique identification is not possible. But if the initial velocity is 0, then it's indeed possible. And if we observe, if we have final observation, then if we reverse time, we can obtain everything, initial conditions and the forces. So that's the conclusion of this presentation. Thank you.
Thank you. Are there questions?